Look up at the night sky on a clear evening, far from city lights, and you are looking at something almost impossible to hold in your mind. Every point of light up there is not just a star, it is a story, a furnace of nuclear fire billions of years old, many of them dead by the time their light reaches your eye. And scattered among those stars, we now know, are planets. Billions upon billions of them. Rocky worlds, ocean worlds, worlds with skies we cannot yet imagine. Tonight, I want to take you on a journey through space and time, through Einstein's universe, through the fire of the Big Bang, through the strange mathematics of string theory, and finally to a question that keeps me up at night as much as any equation ever has. Are we alone? By the end of this, I think you'll agree the universe has been quietly telling us, in its own language, that it should be teeming with life. The only mystery is why we haven't heard back. Let's start with something deceptively simple. Time. We experience time as a river, flowing in one direction, carrying us from birth to death, from breakfast to bedtime, always forward, always at the same steady pace for everyone. That feels obvious. It feels like the most basic fact of existence, and it is completely wrong. Albert Einstein, more than a century ago, showed us that time is not a universal river at all. It is something more like a personal current, one that moves differently depending on how fast you are traveling and how strong the gravity is around you. This came from what seems like a small observation. Light always travels at the same speed, no matter how fast you are moving toward or away from its source. That single fact, when you take it seriously, shatters the idea of a single, shared now for everyone in the universe. Here is the thought experiment that Einstein himself loved. Imagine you are on a train moving at a significant fraction of the speed of light, and I am standing on the platform watching you go by. You bounce a beam of light straight up and down inside your train car, off a mirror on the ceiling and back to a mirror on the floor. From your perspective, that light just goes up and down, a short, simple path. But from my perspective, standing still on the platform, the train is moving, so the light doesn't just go up and down. It traces a longer, diagonal path, like a stretched-out triangle, because the whole train has shifted forward while the light was traveling. Since the speed of light has to be the same for both of us, and I am watching it take a longer path in the same physical situation, the only way that math works out is if time itself is ticking slower for you than it is for me. Not because your watch is broken, not because of some trick of perception. Time itself, the actual flow of moments, is genuinely slower for you. This is called time dilation, and it isn't science fiction. It's measured every single day. The GPS satellites orbiting Earth right now have atomic clocks on board, and those clocks have to be corrected constantly for exactly this effect, because they experience time slightly differently than clocks on the ground. If we didn't correct for it, GPS would drift and become useless within hours. Einstein didn't stop there. A decade after his special theory of relativity, he gave us general relativity, an even deeper idea. Gravity isn't really a force pulling objects toward each other, the way Newton imagined it. Gravity is the shape of space-time itself. Picture a stretched rubber sheet with a bowling ball placed in the middle. The sheet curves downward around the ball. Now roll a marble across that sheet. It doesn't travel in a straight line anymore. It curves, spirals, maybe even orbits the bowling ball for a while. That marble isn't being pulled by some invisible string. It's simply following the curved shape of the sheet, but the straightest possible path available to it in a bent surface. Einstein said the same thing happens with planets, stars, light, and even us. Massive objects like the sun bend the fabric of space and time around them, and everything else, including light itself, simply follows the curves that are already there. This is why time runs slightly slower near a massive object like Earth than it does far away in empty space. It's why a clock on a mountaintop ticks, almost imperceptibly, faster than a clock in a valley. And it's why, near something as extreme as a black hole, time can slow down so dramatically that from the outside, an object falling in seems to freeze at the edge forever, even though from its own perspective, it falls right through. This single idea that space and time are flexible, bendable, part of the same fabric, is one of the most beautiful and most tested ideas in the history of science. Every GPS satellite, every gravitational wave detector, Every observation of light bending around distant galaxies confirms it again and again. And once you accept that space and time are physical things that can stretch, warp, and even tear, you are ready for the next great story, the birth of the universe itself. Roughly 13.8 billion years ago, everything that exists, every galaxy, every star, every planet, every atom in your body, was compressed into a state so small, so hot, and so dense that our current laws of physics simply break down trying to describe it. We call this the Big Bang, though the name is a little misleading. It wasn't an explosion happening at some point inside an already existing empty space. It was the expansion of space itself, everywhere, all at once. There was no center to it, no outside for it to expand into, because space and time as we know them came into being along with that expansion. Trying to picture before the Big Bang is a bit like trying to picture what's changed north of the North Pole. The question itself may not make sense within the framework we'll Taylor using. In the first fraction of a second, the universe went through an extraordinary burst of expansion called inflation, stretching space by an almost unimaginable factor in a sliver of time far shorter than the blink of an eye. Then, as the universe cooled from that initial fireball, matter and energy began to settle into the forms we recognize. Quarks combined into protons and neutrons. After a few minutes, protons and neutrons fused into the simplest atomic nuclei, mostly hydrogen and helium. But it took nearly 400,000 years before the universe cooled enough for electrons to settle into orbits around those nuclei, forming neutral atoms for the first time. The moment that happened, light was finally set free to travel across the universe without constantly scattering off charged particles. That ancient light still exists today, stretched out by the universe's expansion into faint microwave radiation, and we can detect it. We call it the cosmic microwave background, and it is, in a very real sense, a baby picture of the universe, taken when it was only about 400,000 years old. Astronomers have mapped this radiation in extraordinary detail, and its patterns match our theoretical predictions with breathtaking precision. This is one of the strongest pieces of evidence we have that the Big Bang picture is correct. From there, gravity slowly pulled matter together into clumps, and those clumps became the first stars and galaxies. Inside those stars, nuclear fusion began forging heavier elements, carbon, oxygen, nitrogen, iron, atoms that did not exist in the early universe at all. When massive stars died, many of them in tremendous explosions called supernovae, they scattered these newly created elements across space, seeding the next generation of stars and planets with the raw materials for chemistry, geology, and eventually biology. This is why it's not just poetic, but literally true, to say we are made of star stuff, the calcium in your bones, the oxygen in your lungs, the iron in your blood, all of it was cooked inside stars that lived and died long before our sun ever formed. Our entire solar system, including Earth and everything on it, condensed out of a cloud of gas and dust that had already been enriched by generations of stellar deaths. In that sense, the story of the Big Bang is not separate from the story of life. It is the first chapter of the same story. Now, as beautifully confirmed as this picture is, physicists know it's incomplete. General relativity, which describes gravity and the large-scale structure of the universe so well, and quantum mechanics, which describes the strange probabilistic behavior of particles at the smallest scales, do not get along with each other. They are both spectacularly successful in their own domains, but when you try to combine them, for instance, to describe the very center of a black hole, or the very first instant of the Big Bang, where enormous mass is compressed into an infinitesimally small space, the mathematics breaks down. We get nonsensical answers, infinities that shouldn't be there. This tension between our two greatest theories is one of the biggest open problems in all of yours, physics, and it's what led many physicists, including myself, down the strange and beautiful road of string theory. The basic idea of string theory is almost embarrassingly simple to state, even though the mathematics behind it is some of the most intricate in physics. Standard physics treats fundamental particles, electrons, quarks, photons, as if they were infinitesimal points with no internal structure. String theory suggests that if you could zoom in far enough, far beyond what any particle accelerator could ever probe, you would find that these aren't points at all, but tiny vibrating loops or strands of energy, something like impossibly small rubber bands. And here's the elegant part. Just as a violin string can vibrate in different patterns to produce different musical notes, these fundamental strings can vibrate in different patterns to produce what we perceive as different particles. An electron might be one note in this cosmic symphony. A quark might be another. Even the graviton, the hypothetical particle that would carry the force of gravity, falls naturally out of the vibrations of these strings. This is what makes string theory so tantalizing. It's the first framework we've found that naturally includes both quantum mechanics and gravity in the same set of equations, potentially unifying everything into one elegant description. But string theory comes with a strange requirement. For the mathematics to be consistent, for the equations to not fall apart into nonsense, the theory requires more dimensions of space than the three we experience: height, width, and depth. Depending on the version of the theory, needs somewhere between 6 and 7 extra spatial dimensions. Where are they? The leading idea is that these extra dimensions are curled up, compactified into shapes so small that we could never hope to see them directly, existing at every single point in our familiar three-dimensional space, like an impossibly tiny, intricate origami folded into scales far beyond anything we can currently probe. It sounds bizarre, and it is. But it's worth remembering that the history of physics is full of ideas that sounded bizarre at CERN. Curved spacetimes sounded bizarre to people used to Newton's flat absolute space. And yet here we are, correcting satellite clocks for that very curvature every day. String theory remains unproven. We don't yet have direct experimental evidence for it, and some of its critics rightly point out that testing it may require energies far beyond what we can currently achieve. But it remains one of our best attempts at a theory of everything, a single mathematical framework that could, in principle, describe every force and every particle in existence, unifying gravity with the other three fundamental forces of nature. So why does any of this matter for the question of life in the universe? Because everything we've just walked through, the physics of space and time, the birth of the universe, the forging of elements inside stars, all of it points toward the same conclusion. The ingredients for life are not rare, exotic accidents. They are the natural, almost inevitable byproduct of how stars and galaxies work. The same physical processes that created carbon and oxygen in one star created them in countless others across every galaxy we can observe. Hydrogen, the most common element in the universe, combines with oxygen to make water, and we have found water, actual water, ice, and vapor, on moons, comets, and planets throughout our own solar system. We've detected complex organic molecules, the building blocks of biology, floating in interstellar clouds and embedded in meteorites that predate the Earth itself. The chemistry that leads toward life doesn't seem to require some special, rare miracle. It seems to be what happens again and again whenever you have enough time, enough energy from a nearby star, and the right basic elements. And we now know from missions like Kepler and TESS that planets are not rare either. Nearly every star we look at seems to have planets around it, and a significant fraction of those planets sit in the so-called habitable zone, the range of distances from their star where liquid water could exist on the surface. With 100 billion galaxies in the observable universe, each containing hundreds of billions of stars, and each of those stars likely hosting planets, the raw numbers become almost impossible to argue with. Even if life is astonishingly rare, if it emerges on only one planet in a million, the sheer scale of the cosmos means that life should still exist elsewhere, probably in staggering numbers, scattered like sparks across an ocean of dark space. This brings us to what's sometimes called the Fermi paradox, named after the physicist Enrico Fermi, who supposedly looked around during a lunch conversation about aliens and simply asked, "Where is everybody?" If the universe is old enough, and the ingredients for life are common enough, and the number of potentially habitable planets is large enough, then simple statistics suggest that intelligent civilizations should have arisen many times over, some of them potentially millions of years before us, with more than enough time to spread, or at least send detectable signals across the galaxy. And yet so far, we have detected nothing. No radio signals confirmed to be artificial. No unambiguous evidence of alien engineering on a cosmic scale. Silence. There are many possible explanations for this silence, and honestly, I find each one fascinating in its own way. Perhaps intelligent life is far rarer than our optimistic statistics suggest, because the jump from simple microbial life to complex technological intelligence involves so many separate improbable steps that very few planets ever complete the whole sequence. Perhaps civilizations tend to be short-lived, destroying themselves through war, environmental collapse, or unforeseen technological risks not long after developing the ability to broadcast into space, meaning that overlapping windows of detectable civilizations across galactic history are rare even if life itself is common. Perhaps advanced civilizations don't use the kind of communication we'll wishing for at all, having moved on to methods of information transfer we haven't even conceived of yet, the way a civilization from 1,000 years ago couldn't have imagined listening for radio waves because radio itself hadn't been discovered. Or perhaps, and this is the one that captures the imagination most, life and even intelligence are common, but interstellar distances are so vast and the speed of light is such an absolute cosmic speed limit that civilizations simply never have the chance to meet, drifting through the same galaxy for millions of years without ever crossing paths, each one alone in its own little pocket of cosmic time. What I find remarkable is that none of this depends on wishful thinking. It comes directly from the physics we've spent this whole video building up. Einstein's relativity tells us that space and time themselves are vast and flexible, and that even at the speed of light, crossing a galaxy takes tens of thousands of years, which alone might explain a great deal of the silence we observe. The Big Bang and the life cycles of stars tell us that the chemical ingredients for life are cooked up constantly throughout cosmic history in stars scattered across every galaxy. And string theory, even in its unfinished, unproven state, reminds us that the universe operates according to a deep, elegant mathematical structure, one where the same fundamental rules apply everywhere, in every galaxy, around every star. If those rules gave rise to life here on this one unremarkable rocky planet orbiting an unremarkable yellow star in an unremarkable spiral galaxy, there is no obvious reason those same rules wouldn't do it elsewhere too, and probably have many times over. I often think about how strange and wonderful it is that we, made of atoms forged in the hearts of long-dead stars, living on a planet made of the same stardust, have managed to look up and work out the age of the universe, the shape of space-time, and the internal life of atoms so small we will never see them directly. That, to me, is the real miracle here. Not that the universe might be full of life, though I do believe the physics and the statistics point strongly in that direction, but that a small, curious species on one planet, orbiting one star, in one galaxy among hundreds of billions, has found a way to reconstruct the story of everything from the first fraction of a second after the Big Bang to the warped space around a black hole, from the vibration of a hypothetical string smaller than an atom to the vast, silent distances that might be keeping us from ever meeting our cosmic neighbors. Whether or not we ever get a signal, whether or not we ever find a single microbe on a distant moon, the universe has already given us something extraordinary, the ability to ask these questions in the first place and to keep searching patiently for the answers. And honestly, I think that's a pretty remarkable place for the story to be right now. Not an ending, but an open question, written in starlight, waiting for us to keep reading.